Let's talk real quickly about the second method to determine whether or not your data has a linear correlation. So the second method is the p-value method. So in order to understand this method, you need to make sure that you understand the definition of a p-value. And this is really important because this definition is going to come into play in every other topic that we're going to discuss in this class. So a p-value in statistics is a probability. More specifically, it's the probability of getting a sample statistic that is at least as extreme as the one that you get from your sample data. But here, because we're talking specifically about paired sample data, the p-value of interest in this section is the probability of getting a paired sample data with a linear correlation coefficient of R that is at least as extreme as the one that we get from our paired sample data. What do we mean by this? So let's take a look at an example. Let's suppose that you have I'm going to make up some numbers here, but let's suppose that you collect some match or paired sample data, and let's say that your sample size is 50. So you have 50 ordered pair, and then you create a scatter plot, and then from that scatter plot, you calculate the correlation coefficient. And again, in this section, the correlation coefficient will always be given to you, but let's say the correlation coefficient is 0.89. So we see here that it's positive, and that means that there is a positive, potentially positive linear correlation between our two variables. But we want to know if this correlation coefficient from our sample data, right, is strong enough for us to actually say that, yes, our sample data does have a linear correlation. So if we're using the p-value method, the p-value is a probability. So again, this value for now will be given to you in chapter 10, and in later sections, I'll show you how to actually calculate a p-value, but for now, it's going to be given to you, and you just need to make sure you can interpret it. So let's suppose that the probability of getting a correlation coefficient of 0.89 for this particular sample data is 0.003. So a p-value of 0.0003, if I convert that to a percent, that is approximately 0.3%. So 0.3% is relatively small. So the rule of thumb that we use to determine if a particular value or result from a study is statistically significant or not, if you guys remember that rule, we talked about it back in chapter 1, we say that anytime the probability of some value, right, is less than or equal to 5%, or as a decimal, that would be 0.05, then we say that that means that our result is statistically significant because it is a very small probability. That same rule applies here. So if our p-value, so I'll write this down, if the p-value, okay, of getting, right, a certain correlation coefficient, so an R value, okay, is 5% or less, then we conclude that the data has a linear correlation, right? On the same note, if your p-value is greater than 5%, then we say that the data does not have a linear correlation. So in this particular example, because our p-value 0.003 is less than that 5%, so less than 0.05, so if we convert that to a decimal, 0.3% is definitely less than 5%, then we can conclude, okay, that our data has a linear correlation, okay? All right, so basically this correlation coefficient of 0.89, it's strong enough for us to say that yes, there is a linear correlation, more specifically a positive linear correlation between our two variables. Okay, so again, doesn't matter which method you use, whether it's the p-value method or the critical value method, it'll always lead you to the same conclusion about whether or not your data has a linear correlation or not.